to talk about some tools that I'm building. So those tools are like maybe 30% ready, rough edges, many things don't work. And this presentation, you see, it's 3 parts, but actually it's like 30% ready. Nevertheless, I think this is one of the best slide decks I've ever made. Let's see how it's going to unfold. I do a lot of graphics programming because I like to interact with things, and graphics programming is very fun. So usually tools that people use for low-level graphics programming, meaning that you want like a lot of control, you want to know where bits are stored, where data goes in and out. When you program, basically, when either use a high-level framework which restricts your capabilities, or you use low-level hooks in this high-level framework, and you always end up doing something like this. So this is the amount of code and actions that are needed to be done in order to draw this beautiful like cube on a cube. So GPU programming is all about setting up a lot of data buffers, nested data structures, compiling shaders, binding textures to frame buffers, binding everything. Huge mess. And whenever you do any change, you make change 3 times. First change is in your shader code that runs on GPU, then change on your CPU rendering code, and this change in your CPU initialization code. So that's why, in order to quickly iterate on interactive experiments on artificial life, I wanted to get a tool that would hide this mess while giving me the low-level control of the computer. So this is where SwissGPU started. SwissGL started. So SwissGL, as of now, is a tiny, like 28 kilobyte uncompressed JavaScript single file library, and this is like the minimal HTML page that like loads and draws something, and it consists of a tag that includes this library. Then a bit of initialization. So I'm trying to shrink this boilerplate smaller and smaller. So eventually this probably like going to be like single line boilerplate. Now it's 4 lines. And the rendering code. Rendering code, which draws this spiral, is a cryptic mess of nonsense. But somehow that's how I started to program when I started programming those things. And if you know Shader Toy, most of shaders on Shader Toy are this sort of nonsense. And I suspect that maybe this is not the because of like well, I don't know why it happens, but actually math papers are also a lot of nonsense. They also use single letter or like single letter variables. So I suspect there is something convergent evolution of notation between shaders and math notation. Okay, so let's try to step by step learn how to use this thing. So the main like principle I wanted to put in the API is that simple things must be easy to make. So like in order to draw a quad, you don't need to make a vertex shader, fragment shader, vertex buffer, fragment buffer, like whatever. You need to say that I need to draw, which means call to this GLSL function. And I want a fragment program, which FP stands for fragment program. And fragment program in its shortest form returns an expression that is evaluated as a vector of 4 floats, so vec4. So this is UV coordinates that occupy first 2 values of this vector, and 0 for green channel, 0 for blue channel, 1 for alpha channel. So we see a quad. We can also, if we don't want such concise and incomprehensible syntax, we can expand things a little bit. So actually, SwissGL expands this code, well, into something much larger, but first expansion looks like this. It wraps the code in a function called fragment, and in this function, we must assign what we want to draw for a particular pixel to a variable called fout. So we have this function is executed very efficiently on GPU for every pixel on the canvas, and we have some variables in our disposal, like UV, that gives us coordinates of current pixel on a quad in 0 to 1 range. And unfortunately, lower left corner is 0, 0 is origin in OpenGL and in WebGL, and it's super annoying because everything disagrees with all other conventions. And in WebGPU, they kind of fixed it. But maybe I'll talk about that later. But now let's see what we can do with single quads. So this is what whole shader toy community is about. It's about drawing a world with two triangles that cover the full screen and writing a function that given point position returns the color that point should make. Also, this happens to be like somewhat tangential with hot topics of neural-based rendering these days, where you have neural networks that map trained to map position of a point to color or to material properties. Here I replaced the expression that is executed for every pixel with this string that uses XY variable, which is the same as UI, but for convenience has range between -1 and 1. And now I take this length of this vector, which is the distance from origin subtracted to 1, take square root, and we have this nice circular blob. Well, it's not circular, it's stretched. I'll talk about it later, a bit about it later. Also, we have another input, which is I, that is coordinates of current pixel, like integer coordinates of current pixel. And those are very handy when we are writing two data textures. I'll talk about it later. And this is the nice bit carpet, they call them. Patterns that are created by very simple binary, very simple expressions. Okay, so now about stretched ellipses. So usually I want visuals to look good on variety of displays. That's why maintaining, taking the viewport aspect ratio into account is very important. That's why there is special keyword that's called aspect that tells whether the quad that SwissGL is going to draw going to fit the viewport, cover the viewport, or maybe cover particular axis of, cover particular axis of the viewport, such as XY. This design may change in the future. I'm not super happy about it, but that's what it is for now. So, for example, if I want to fit, I'm saying that I want my quad to fit the viewport. We can also animate stuff easily by passing the data from JavaScript side to GPU side. So here I say that shader will have access to a variable called R, which stands for radius, that depended on time, and this code is executed on JavaScript side, and then implicitly made available on GPU with the scalar variable of the same name, and position here just hard-coded as a vec2 and gets also submitted to GLSL side. So we see that this blob is now shifted, and we also see, and actually the first argument of GLSL function, like everything that is not a special keyword, is treated as a uniform. So SwissGL will try to capture the value of input and pass it to GPU. Okay, but now why top and bottom are trimmed you see that there is those black bars here. That's because the core of SwissGL is a quad driving library. Well, it may sound kind of restrictive that this library can't draw anything except quadrilaterals, but GPUs can only draw triangles, so SwissGL is more powerful than GPU itself. And there are some special functions that help to analyze debug meshes. So this wireframe helper function can produce this pixel thin wireframe lines so that we know which geometry we are rendering. And by default, if we don't tell it anything, it draws a quad that fits like -1 to 1 coordinates. And like if we don't pass aspect, this covers full viewport, but aspect modifies the device coordinates so that X and Y have the same scale. Then also we can't draw outside of this quad with a fragment program, because fragment program only tells GPU what to draw, but doesn't tell where to draw. It's like function from pixel coordinates. But if you think of like shader toy, then on shader toy, that's where things stop. You don't have any capabilities more. Like you have to figure out how to deal with this. With SwissGL, you have access to vertex programming. So fragment program tells what to draw, and vertex program tells where to draw. So here we also have, so I also pass time variable as a uniform, and then I can take the compute some point that is depending, well, actually, okay, so vertex program, fragment program, and now a bit decrypted version of the same code. So here I have time variable, then I can use it to compute the center of the quad. So this vertex program is executed for every vertex, but these uniforms are shared by all vertices, so value of this vector is the same for all vertices, and then I can apply offset that would shift a particular vertex away from the center, and now we can position primitives we are drawing. This may not sound super impressive, but this is the foundation of everything I was doing, like all the simulations I was doing over the last couple of years. So we can apply rotations. There is this handy function that taken an angle expressed in radians produces the 2x2 rotation matrix. So I can just do this multiplication that multiplies matrix by a vector, produces another vector, and gives more flexibility. So, but if quads are boring, then SwissGL can tessellate quads. So it's quad drawing library, but it can draw tessellated instanced quadrilaterals. So let's try to decrypt those lines. So there is single call that draws this strange worm. And the first thing to take into attention is this mesh keyword. It means that I want to tessellate the primitive I'm drawing to 64 chunks, 64 segments in X dimension and 1 in Y dimension. Then I wrote a function that will tell the trajectory this thing moves. So given t, which like time, it just some function that determines the trajectory. And now for a particular vertex, I take current time value and then subtract the x coordinate of a particular vertex in a quadrilateral, so that I can shift those segments in time forward to backward. And then I can sample the position of a center of a particular segment on the path. Now I need to take the like offset this position. Oh, and by the way, this slide deck is available. So if you want to like open it on your computer right now, you can just like go to this link and play on your computers and tell me that nothing works, so that I know which platforms are not supported yet. Okay. So now I need to offset vertices from the path. That's why I compute tangent. If I were not that lazy, I would have computed derivatives manually, but I'm lazy. That's why I just take finite differences. So like I take a point, little step forward in time, and subtract center from that point, normalize, and then rotate 90 degrees. Now I have normal. Then I compute width of this segment, which once again depends on the x coordinate. And I compute offset, which is width of the segment multiplied by y, which is -1 for like left side of the snake and 1 for right side of the snake, and multiplied by normal vector. So now I'm ready to produce my vertex position, which is center minus offset. And I use the same fragment shader to like paint the primitive. I can also add some texture by using different fragment program, and here I'm just using cosine of y coordinate to make those stripes. So with I think main point here is that although this library is super low level, actually whenever you want something like non-usual, like arrow of some strange form, some plot with like some diagram that looks not as just like some dashed line, but anything non-standard, you'll end up fighting with the library, with high-level library you're using. But turns out that actually implementing most of the primitives doesn't take that much code if you are doing it low level. Okay, so of course we can also tessellate primitives in 2 dimensions. So here I am tessellating the quad 8x8, computing the offsets, and here is this displacement that depends on x for y. So I use this Switzerland syntax from GLSL to swap coordinates. That's why like y offset depends on x and x offset depends on y. And yeah, we have this flag. And you may notice that this tessellation pattern is a little bit strange. And this is deliberate. I wanted to be able to produce triangular meshes easily. So this little cryptic code interpolates between standard XY and this like shrinked shifted XY that gives you a nice triangular mesh if you want to render some height map, anything. Okay, now we learned how to draw a single quad. Let's draw many things. And of course, like traditional way is using for loop, but we are not using for loops because for loops are slow on JavaScript side, and we want fast 120 frames per second, everything. So we are going to use a technique called instancing. It's when we tell GPU to draw many things at once. And there is a special argument as usually. It's called grid. And now I say that I want instantiate the primitive I'm drawing 8 in like 8 in 1 dimension and 8 in 2 dimension. Actually, grids may have up to 3 dimensions in SwissGL. So overall, I'm going to draw 64 quads. And there is inside of the shader, inside of the vertex program, we have access to instance information in form of ID, which is the index of the current primitive the current vertex belongs to, and the size of the grid. So here I compute position of the primitive depending on its index and the size of the grid. Then I also use the computed position to animate the radius of the quad. And as we've seen before, I transform this 0, 1 to -1, 1 range coordinate and apply offset similar to what we've seen already. And also we can pass data from between stages of the like graphics pipeline, so from vertex program to fragment program. And behind the scenes, we saw that XY and UV can be used in both vertex and fragment programs. That's because they are SwissGL implicitly like as this boilerplate that passes vertex and shader coordinates. But we can also compute color. So here color is computed depending on the radius of the primitive. And there is this keyword varying that we can use, saying that I want to make this variable available in fragment program. And in fragment program, I simply use it value. And then about random numbers. So sometimes things look nice when there is some randomness involved, and in simulations we often rely on random numbers. Here in GPU programming, there is no like random function, but people typically use hashes. So this hash function, which is part of SwissGL tiny standard library, is taking three-dimensional integer vector and produces three-dimensional vector of floating point values from 0 to 1. Also, there are some constants defined, like tau, which is 2 pi for convenience. So here I produce a vector of 3 random numbers. Then I use those random numbers to compute the phase of animation for a particular quad and the frequency of this animation. I compute the radius. And then like the rest is same with the previous shader. Also, grid and mesh arguments work together. So we can draw instanced and tessellated primitives at the same time. And also here I shift phase by the distance of the vertex from the center of the quad. So we see that different vertices of the primitive now have different. This projector is so dim. Can you turn off this light?
Yes. There is a switch.
We can turn off all lights.
That's fine. I mean, we have a lot of. And also, maybe is it possible to close blinds a little bit? No, I think it should be some. Yeah, there is a black blind, but that's how it works. Okay, I was expecting to see some. How will it work?
Stop, also stop.
And
This one's stuck. I'm sorry.
okay. Okay, I think I made it worse. Okay. Okay. Now a few words about 3D. This cube has 6 faces. That's why in SwissGL we draw cubes with 6 quadrilaterals. Now there is this helper function that takes the index of corresponding face and like XY coordinates and produces a three-dimensional vertex. So now we can apply some rotations to this vertex, colorize it using the coordinate of the center point of that face, which is normal. And we have like cube in 3 dimensions, but there is a problem. This problem is that primitives are drawn in order, not from like far to viewer, but just in order they are created, and we can easily solve this with enabling depth test. And also, we can use special arguments like face front or back, saying that we want only forward-facing or backward-facing face of the cube, but we can't distinguish between them because there is no perspective. For perspective, people typically use like so-called projection metrics, but I was hesitant to add the metrics library as a dependency to SwissGL. That's why I am using this like a weird one-line trick that just does what projection matrix multiplication was supposed to do for you. Basically magnifying stuff that's closer to viewer and closer to the camera, and shrinking stuff that is further away from the camera. And like in all graphics libraries, this is handled by assigning values to this last coordinate, and then GPU divides XYZ by this last coordinate. So this is like little technical detail, but now we have cubes. We can easily instance them and draw 1,000 cubes for the price of one. So I use first dimension of the grid to index the faces and second dimension to index the cubes, and then I use hash to shift the corresponding cube using its cube index. We can also pass different values to different corners of the cube, and we can get nice color cube. Then difficult topic, surface normals. So we are used to seeing things that are shaded with light. So I didn't implement any lighting here, but it's not super like difficult with a few lines of code. But I thought that like interested user can do it themselves. But normals are still needed for this, and I made a special like helper, like surf macro that allows to easily compute normals. So here I say that I draw a cube with 6 faces. Faces are tessellated 32 by 32, and then I define a special function that takes UV like XY coordinates from -1 to 1 and produces the position of a particular of a corresponding point in 3D space. And then this macro is given the function we want to draw, the XY position of the vertex in a quad. Then it stores the resulting normal to a given variable, and you need to pass epsilon. So you see again that we are lazy and just do infinite differences. So internally it would call this function 3 times to determine the position, and also advance a little bit in x dimension and y dimension by epsilon, and take cross product. So do this standard vector math to compute surface normal, but at least we don't have to do it ourselves. So then we assign the output of this function to the vertex position, well, also doing this perspective division. I'm ignoring that. And normal is automatically stored in this variable that is varying, though, so it's available in fragment shader, and we use it to colorize the surface. So we see that like as if it's like faces looking upward are green, faces looking right are red, faces looking to us are blue. And the way this surface function works is, well, it's some trickery to make this like pillow-shaped surface, and then rotation is applied. So that's why surface coordinates are computed in walled space. So we get normals in walled space, in which it's like easy to shade. Then okay, back to the plane. We already know that we can draw quads, that we can animate their position. So now we like take random number, compute position of a corresponding quad along the path, apply some random shift to this position, and then we colorize the internals of the quad with this function, which is exponentially decaying from the center, but we don't like this annoying black boxes. The boundaries are still opaque, but there is a mechanism in graphics called blending to fix this. So blending is a little mini language. There is ugly 20 line of code, regular expression based like compiler in the library that parses such strings into cryptic like WebGL parameters to a few WebGL functions. So this expression uses S and SA for the color and alpha of the source, which stands for incoming, for the primitive that we are going to draw, and D alpha for the values that are currently on the buffer. So then we overlay those values to the buffer, and like simple mode, such as like D plus S, stands that we are just adding colors of the values that are coming. Then this is like standard alpha overlay when we draw primitives from far to near, and we want them to be semi-transparent. So we multiply. This is a coefficient how much light can pass through the primitive, and this is the opacity of the primitive itself. There are also some other more exotic methods. In particular, this is very useful. You can compute minimum and maximum of two values, and this produces nice Voronoi-like patterns. So here there are points spinning around, and we see clearly that they produce a Voronoi diagram, because shading uses maximum between a color produced by a new primitive and what's already in the buffer. Now stateful computation. This is yeah.
Can you explain a bit more what is S and D, like in this example?
Where?
S and D.
Once again, these are source and destination. So you have a texture buffer, and then primitives are drawn to it. So in texture buffer, there are some values already. Okay. For every pixel, we have like destination RGB value and destination alpha. And then the primitive you are drawing, the output of a fragment shader is also a source, like RGB and alpha. And blending expression tells how GPU is going to combine the two. So ideally, in ideal world, this would have been just part of a fragment shader, but unfortunately, in all the days, like hardware had special units that were responsible for fetching data, like for combining data that produced by those shading units. Okay, so and here those like S&D, this is just like mini embedded language that says that when I'm blending, I want maximum between those values. Okay, so finally, stateful computation. So far we were doing only like functional visualization, where you have input variables and they map to a particular image, but you can only do some like prescripted animations this way. For simulation, we want to store data on GPU somewhere. And in graphics, the like usual way of storing mutable bulky data are textures. So we will use textures. Well, in modern APIs, there are compute shaders, but unfortunately here we are restricted to WebGL 2.0, which doesn't have any compute shaders involved. I'll talk about WebGPU a bit later, very briefly. But here, like very simple use case, I want to pass data from CPU side to GPU. Oops. Oh, wow. How did I end up here? One moment.
36.
35. Okay. That's why, so I create array that has some constant values and some value that's varying over time. This array has 4 elements, and then I say that I don't want to render anything, but there is this second argument. So in SwissGL, first argument is what to draw, and the second argument is all about where to store the result. And here I say that I want to create a new texture that will have a single channel 8-bit format, will have size 2x2, and will contain these data. And all textures must have a tag, because that's how SwissGL will figure out on the next frame that this texture was already created, and now all it has to do is upload new data to this texture without recreating it from scratch. And now, once texture is created, and so this whole loop is executed at every frame. And this is the one of points of SwissGL, so that initialization must be as close as possible to the point where you are actually using the structure you created. So that you don't have separate code that creates a texture somewhere and then code that updates this texture in a loop and code that uses this texture. So they are all merged. And now we can pass this texture as uniform, and inside we can query this texture using function called syntax. So texture queries always return tuples of vectors of 4 elements. So I just draw the R, which stands for first element of this vector. Then we can also stream videos to textures to do some processing. I'll show later some demos that use it. Also, we can use this the same syntax to upload images to GPU, say like textures, font atlases, so that if you want to render text. And also, I had to flip the image so it's not upside down because of GL conventions. Okay, but this is not that interesting if you couldn't produce textures on GPU themselves. The whole point is that we want to offload computation, very parallel heavy computation to the GPU side. And this is where render to texture comes into play. So here we are just drawing some spinning quadrilateral, but we add this argument that says that we want to allocate texture of size 64 by 64 that will detect RTT. And behind the scenes, it will create a lot of structures. It will create frame buffer, create textures, attach them to each other, make sure that it reallocated if texture size is changed. But tag allows SwissGL to keep the reference that this is the same render buffer I'm going to render to, no need to create a new one. And then we can query this buffer like a normal texture. But you can notice that there is persistence. So by default, canvas gets erased every frame, but that's not the case for those render buffers. That's why they can be used to store state that propagates across frames. But if you want to remove the state, we can use clear argument that would just clear the buffer before the draw call. We can give a color, or we can give a single value that will be spread across all channels of the texture. Also, sampling texture. There is a sampler mechanism that allows you to say how you want to sample the texture. For example, by default, we use nearest neighbor interpolation with repeat wrapping. But here I say that I want to clamp to edge. So I sample the same texture with two different samplers. One is linear interpolation, mirror repeat, and another is nearest neighbor with clamp to edge. And depending on the y coordinate of the pixel, I select between two samplers, A and B, which all refer to the same data. Okay, now the main part is data textures, which can store the state that is not only color but some higher precision values, like floating point, like 32-bit floating points. And here I compute some positions on a plane using hash function, and I store those as pixel values. But I tell SwissGL that I want a texture that stores floating point values. That's why when I draw it, even though I divide it by 6, you see that pixels are fully saturated. That's because usual textures store values between 0 and 1, which represent color channels, and here you don't have, you store arbitrary 32-bit floating numbers. And we can use this data later to control position of the primitives. So here I take this points texture and I pass it as a uniform, and I also use its size as the size of the grid. So I'll draw as many primitives as pixels in this texture. And then every vertex programs can also query textures. That's why I call points, and notice that I'm using integer coordinates here. So this ID is integer vector, and there are two overloads of this function. If you pass floating points, then they assume to be in a range from 0 to 1, like usual texture coordinates. If it's integer value, then these are just pixel coordinates. And I extract XY value, and I compute on-screen position, and I get those quads that are positioned corresponding to values stored in this buffer. Now we can do some animation that depends on previous position of the particle. So unfortunately, with WebGL, you can't render and read the same buffer at the same time. That's why there is a common technique called ping-pong buffers, where you have two instances of every buffer, and you read one of them, write one of them, then swap them around and do the same again. And here there is a special texture parameter called story. So story 2 means that we will create a ring buffer of 2 snapshots of the texture, and on every draw to this texture, they will be rotated. And then we bind only one of those 2. So here I say that I want buffer number 0, which is the last one. And then during the simulation, I have SwissGL, whenever it sees that it's going to render to this buffers that have history, adds special uniform called ASRC, which allows to query previous values from the buffer, so values from the previous call. And I read the current position of the particle. Also, there is this frame count variable, which I reset on every click to the canvas. that I used to initialize. So whenever frame count equals 0, I discard this value and just compute random starting position. And then I compute velocity that is based on a current position of the point. I just rotate it by like 90 degrees. And I store the new position into the buffer, which is like position plus velocity. Okay. Now let's make particles interact. I added like simple repulsion, and this repulsion is implemented in the dumbest possible, very slow way. But on GPU, everything is so parallel and so fast that actually, well, for large-scale simulations, spatial indexing structures are needed. But often for moderate numbers of particles, it's just faster to compute everything in O n squared algorithm, and it does the job. So what happens here is that for every particle, I take a two-dimensional for loop that iterates. There is this variable called view size that gives pixel size of current viewport. And whenever I discover myself, I just skip that pixel. Then otherwise, I read the position of other point, subtract my position from it, and get the like displacement vector from myself to. So this is executed for every particle. So every particle reads all other particles, and I compute the distance to other particle. I normalize the displacement vector and do like simple repulsion. This is the repulsion contribution that other particle produces on ourselves. Just subtract displacement vector multiplied by this coefficient, which decreases if r increases until it iterates to 0. And I just accumulate velocities from all particles to this buffer, to this variable, and apply it to current position the same way. So now, okay. Yeah.
What would be the order of magnitude of a moderate number of particles on an average machine?
Like 1,000. Well, 1,000 is reasonable. If you, well, maybe a couple of thousand. So if you, there are ways to process millions, but for millions you need fancier data. Yeah.
Is okay to
well, actually, for different hardware, like it depends on hardware, and I've seen cases when on like TPU simulations, those like tensor processing units for training neural networks, people were preferring quadratic algorithms for tens of thousands of particles just because it was like much faster than trying to make this dumb thing do anything fancy, which requires sparse memory lookups. So like raw computing power is quite abundant these days.
For that code, every particle calculates the distance to every other.
Yes. So of course this hurts people who used to like classical well-optimized programming. Yeah. This hurts. I understand that. Yes. So here is like walk through this little like putting things together. I wanted to at least, so this presentation got quite technical, so I wanted to put at least some artificial life here, and that's why I finally like put all the pieces together, and let's like walk through this code. So this is yet another particle linear. This particle linear variant uses multiple fields, but they are all radially decaying fields. And so simulations are performed in a loop. For every frame, I do 10 update steps and then do rendering. And in my update step, well, also I use current time as a seed. Well, value derived from current time as a seed on initialization. So every time I click the canvas, we get like different initial arrangement of points. And then, okay, this is the initialization code. And this variant of particle linear maintains 3 fields and 3 gradients of this field. I use 3-dimensional points here just because there is this nice symmetry between 3-dimensional points. And also at some moment I had 3-dimensional version of this simulation, but then I discarded it. That's why like those vectors stick. But we have 3 values, accumulated values from fields produced by all particles, and we have 3 gradients of those fields, and then every particle computes contribution of every other particle to the field to all 3 fields in its position. And there are those S2 which control the like speed that each field decays. So I assume these are like 3 different chemicals that diffuse with different velocity, for example. And then so I compute vector of 3 field values. I compute vector of 3 derivatives of fields produced by this one particle we are looking at. And then I accumulate the contribution of the other particles field to my position in space, and I compute the accumulate the gradient of those fields by using the displacement vector between my particle and that other particle. And then for this simulation, every particle wants to stay at spatial location that has values of those 3 fields having particular basically particular values of those 3 fields. So it's happy when it has it's in particular condition. Otherwise, it tries to follow the gradient of those fields to get into position that has the desired like concentrations of those 3 chemicals, and this leads to this tentacle-like dynamics. So not much principled study about this. I guess Bert knows way more about this sort of systems. Here is just an example of simulation implemented entirely in shaders in like 38 lines of code. And I draw particles 2 times. So first time I render those glowing fields, and then second pass with like maximum blending renders those white particle positions. Okay, now I think I'm done more or less with SwissGL side or part of the presentation. Just wanted to show this little demo, and now I think like it's easy to understand what kind of SwissGL like calls and primitives where no, I can't. Please look at your laptop screens. So it's easy to see that this is probably a reaction diffusion simulation. So there is a ping pong buffer that just does diffusion and, well, classical Gray-Scott reaction diffusion. And then there is a single call to this grid, the tessellated grid primitive, and every vertex of that grid makes a lookup to the buffer that stores the current state of 2 chemical concentrations. And then there is a displacement that is computed for every vertex, and color that is passed to fragment shader using the uniforms. So yeah, and then there is this website with well, I guess many of you have seen, with a bunch of other demos, and for every demo there is a link to the source code. And well, this iframe doesn't give me camera. But speaking of scale, so this is like example of linear with a few hundreds of particles, but here linear with 10,000 of particles. And to implement this variant, that unfortunately is not performant enough to run on mobile phones, although hardware is capable, but these are like more restrictions of WebGL API that makes it difficult to implement efficient spatial indexing. But here, to do spatial indexing, I sort positions of all particles in X and Y directions. There is like a buffer that stores position of particles, and they are sorted column-wise and row-wise. And then I, for each particle, just scan the smaller rect within this large rectangle that stores positions of particles. But then another way to accelerate computation that has a lot of particles and needs local computation is using textures. So this is like classical Physarum polycephalum simulation, and here I rasterize all particles in off-screen texture. And then I have a separate path that diffuses this texture by averaging values of adjacent pixels. And then every agent does texture lookups to this texture at 3 different positions and decides whether to turn left or right depending on the values of those 3 lookups. Okay, where is my zoom? Yeah. Zoom. Yeah, and this I don't remember how many particles are there, like maybe a few tens of thousands, and this runs like this one is super performant. Yeah. Okay, so and the implementation is also quite compact. For example, so the update step, this part updates the texture. This is the diffusion implemented with a few lookups to the same texture. And then this is the logic of the agent that does 3 lookups, and then comparing the values decides whether it wants forward or left or right. And then slightly fancier variant. Let me check how many particles are there. Okay, agent positions, 256 by 256. So not that many. I have 64,000 agents, but here, unfortunately, on WebGL 2, it's impossible to render to 3D textures. That's why you can render to slice, but here I just pack the whole volume into one 2D texture to render all pixels at the same time and diffuse them in the same time. And yeah, this is like 3D version of the same Physarum. Yeah, this is the volume, and these are agents. Okay, well, also there are like canonical graphics tricks like deferred shading, which is impossible to see on the screen. Yeah, and well, obviously, game of life. This one, most recent, and the one I'm quite happy about. This is this classical synchronization of fireflies. So there is this circle, and every agent has a little clock running and like oscillator, and whenever oscillator hits particular phase, then it blinks, and whenever it detects there is a blink nearby, it nudges the oscillator a little bit, and this very simple algorithm allows fireflies to synchronize, although they're like globally synchronized, although their perception radius is quite small. So if we wait a little bit, we'll see that they've they reached full synchronization, which is very nice to observe. And also, but of course, if we decrease the radius, then I guess it would take. Oh, they can even do it with very small radius. Nice. Yeah, and well, there is some other parameter. Well, and with large radius, of course, it's very easy for them to fit. And we see that this simulation is super performant, and it's also using a texture for communication. So whenever agent wants to flash, it just draws a frame, draw points. So this step function, whenever agent wants to flash, it draws a quad in a special off-screen texture of size 256 by 256, quite small buffer, and then it reads this texture to figure out if there was a flash nearby. And this sort of communication is very efficient on GPUs without having the need for fancy indexing structures. Okay, now this stuff, SwissGPU, is very unfinished, experimental. Unfortunately, I'm not ready to give a tutorial on using it, but I can talk. Oh my God, let's reset. I can talk about the paper briefly that we released a few weeks ago. Oops, I closed my tab. And this paper, so now a little part about A-Life. Let me quickly explain what's going on here. So here there is a soup of tapes of 64 bytes. And on each step, those 64 bytes tapes get, at first they're all initialized with random characters. And then they are random pairs of those tapes concatenated and executed from left to right as programs in a language that's called brainfuck. This is a very simple esoteric language that allows to specify the Turing machine. So essentially, these square brackets are used to create loops. And okay, magic happened before I managed to explain what's going on. So the idea that we have random programs, we concatenate those programs, those programs are executed and they modify themselves. So whenever the code tape and the data tape are the same tapes, so both code tape, code head and data read-write heads traverse the same. And we have soup of random garbage that modifies random garbage to produce random garbage. And then whenever two particles, two tapes interact for a number of steps, we just split them and put back to position in the soup where we took them. And at first we observed that, well, this is simulation deterministic. That's why I know when transition happens. Transition will happen on the step 9000. And here every pixel corresponds to one character in the soup, and green corresponds to bytes that encode BF language instructions. And here the close-up of a few tapes from here. So we see that's what and also there is in parallel, there is a process of random mutation. So some bytes get flipped in the soup randomly. And interestingly, so this evolution without any purpose, without any objective, accidentally produces a program that can copy itself to the other part of the tape when they concatenate it. And then once it happens, everything changes dramatically because the whole soup becomes replicators, and these replicators start to compete with each other to become more and more robust to noise. So before there was no objective, and then suddenly the more resilient to noise replicator survives. If you wait longer, they will become shorter and shorter. And in this paper, we studied a number of different languages. So in addition to BF, here we analyzed the trajectory, how replicators happen when the first replicator appeared, and the process of emergence of replicator is also quite interesting, because turns out that it's not, well, we are not sure how universal is this, but probably it's not random mutation that produced this particular replicator, but a lucky coincidence of self-modification when a loop got produced by concatenation of two tapes, and then this loop copied itself in reverse order to produce reversed replicator, and then copied the reversed again to produce the full replicator. And well, quite fascinating dynamics, although we are not yet sure what we are dealing with here. And from a technical perspective, this particular simulation you are seeing, well, I thought it as a challenge to study the new API, because WebGL, well, WebGL is essentially exposes capabilities that are available on desktop computers for about 20 years. So Web is when 20, no, yeah, Web is 20 years behind native, and Web GPU exposes capabilities that are available for maybe 15 years. Okay, so maybe WebGL is 25 years. Okay, yeah, so it's about 10 years of advancement. But I'm not that worried about using ancient technologies, because next I'll talk about using technology that is 50 years old. No, yeah, about 50 years old. But okay, getting back to this. So this is my attempt to make a framework that would allow to write programs that run on GPU using syntax that is as close as possible to JavaScript, which is strange attempt, but nevertheless. So for example, BF machine simulator looks like more or less standard JavaScript. We have a tape, we have a pointers that traverse the tape, and then depending on what they see on the tape, they change the state of the machine. They can, whenever it wants to increment byte, it just increments particular byte in memory. And this is something that gives a lot of freedom in comparison to GLSL shaders, because in shaders you don't have scattered writes, you have scattered reads. You can control where you read from, but you always write one pixel. And here with compute shaders, you finally have more freedom, and that allowed me to implement this web BFF library running in browser. Okay, then next thing. So this thing is even when I told about using ancient technologies. So Z80 CPU is a CPU that got developed in, I don't remember, I think 1970. It got introduced in 1979 and got discontinued in June this year. So pretty much the same variant was manufactured, well, with a little bit more advanced process, was manufactured for almost 50 years. And what happens here, actually it's better to show. Unfortunately, this is the part which I really rushed to get ready before the conference, but couldn't. So it's not yet exposed on the web. But what happens here is you have a two-dimensional grid where every cell, okay, let me draw. So you have a two-dimensional grid, and every cell is a 16-byte memory buffer. And then there are the Z80 CPUs that are attached to adjacent cells. And sometimes, like initially, this memory is full of garbage, and stochastically, one of those CPUs, whenever it sees that adjacent tapes are not occupied, are not processed by any other CPU, then this CPU just concatenates these two buffers in random order into one 62-byte memory buffer, and executes the content of this buffer starting from the beginning and freshly reset CPU state, and all memory requests that fall outside of this buffer get wrapped into the same 32-bit memory space. That's why code pointer just spins around the buffer many times. So this is what like typically pre-transition soup looks like. So we see that there is a lot of garbage programs. Sometimes they often produce repeating byte values, but these byte values can't replicate themselves to adjacent cells. And in order to visualize the Z80 assembly, I tried to make this sort of atlas where it produces visual mnemonic for every byte. For example, these are move instructions that sends later from register A to register H. This is like stored memory instructions, and very important, this is a stack pop, and this is a stack push instruction that takes pair of BC registers and push it on stack. And stack grows from the last addresses, from the end of the address space in Z80. That's why the first replicators emerge quite quickly, because of a lucky combination of like store immediate value to register. So these 2 bytes get stored into register. Actually, I have somewhere we have it. No. So this is the emergence of the first replicator, and that starts replicating itself. There is instruction that stores, for example, like stores 2 bytes in the register D, and then instruction that pushes this D on stack. And then whenever this replicator is produced, then it's like a little bit damaged, but it's functioning. So, and then everything changes because this replicator starts to colonize the grid of Z80s. And but like it would have been boring if it only flooded the whole grid with the same replicator. Actually, the story that happened was quite more interesting, because when replicator tries to copy itself to some some background noise cells, they may contain values that damage the replicator. So and eventually we have some cells that can't be properly copied by replicator. So but when replicator tries to copy them, it damages itself. That's why without noise, actually the grid would have been full of not replicators, not functioning replicators, but those dead, destroyed replicators. So this is like a sort of disease that the first generation of replicators are affected by. And then luckily we have noise, and this noise little by little destroys these damaged replicators. They decay and produce this grayish ground, so that the first generation replicator can come back into. And so we see that those green damaged cells degrade, and then replicators colonize this space again. And then we, like in the first, after the first transition, we observe a lot of those waves that traverse the grid again and again. But actually, in this particular simulation, there are other things happening afterwards. So there are at least there are at least three kinds of stack-based replicators emerge, which use different set of registers. And let's wait a little bit. So this is the now like the soup is happy being traversed by waves of replicators. But then around here, a new breed of replicators emerged. They use different registers. So they use HL register, and I colorize them differently, and they start to spread. And then there is another set of replicators that use BC register. And then those three breeds compete with each other. But there is another thing. I didn't yet analyze how it works. So these replicators, they use a bit different mechanism, also stack, but they look up from the do indirect memory lookups rather than using immediate values. That's why they seem to be more robust, and they seem to be in some sort of mutually beneficial relationship with other stack-based replicators, because they help to clear the ground from damaged replicators so that other replicators survive. So the soup is very active when they are present in parallel, this type of replicator and the first type of replicators. But then another thing happens. So here we see a totally new type of replicator spreading. And this is where evolution found basically a MEM-CPI instruction. So in Z80, that is inspired, instruction set expired by 4004 CPU. Basically, there is a that 2-byte instruction. When particular 2 bytes are combined together, they form a loop that continuously copies the memory values from location pointed by one register to location pointed by another register. And we see that, if I go to the boundary, so for example, here we see that execution got stuck in this particular location. So the code pointer stays at the same position, and memory is being copied again and again. And this type of replicators overtakes the soup eventually. And well, in different wall, if I take a different initialization seed and try to reset and play, here we have different dynamics. So stack-based replicators appear almost instantly, and then there is a different kind of more successful replicator that I don't fully understand yet. This new replicator uses some different mechanism. It's something about those exchange. So this exchange instruction exchanges the top of a stack with a particular register, and somehow this also becomes very competitive and overtakes the grid. And actually, there are a few variants of this. I might just my color map is not that good. Maybe if I, for example, C9. Did I visualize it? Yes. 7.7. Let's visualize 7.7. Oh, I broke something. Sorry. Okay, it doesn't work. Okay, but this is a bit similar to Code Wars, very old, competitive assembly environment, but with the difference that we don't explicitly create replicators. Turns out that in a very simple configuration, replicators emerge out of chaos quite easily. Interestingly, this first generation this white replicator is not efficient on its own. So stack-based replicator, like green, red, or blue replicators colonize the grid very quickly, but white replicator somehow only effective when there is other replicators around. So we see some sort of symbiosis, we see some sort of virus-like behaviors, and we see some sort of evolution in the technology that was available for 50 years. So 50 years ago, we could make such a grid, and it will produce those replicators. And now we can, from technical perspective, this simulation is performed with. This is a combination of WebAssembly, where I took the open source Z80 simulator. So this is like open source Z80 simulator that is compiled to WebAssembly that runs on CPU, and then so this is my CPU modules, and then on GPU, like I use SwissGL to render this grid. And I stream the data from CPU buffers to GPU, like the same way I showed today. And I use fragment shaders that, depending on the value they read from instruction text, to fetch different tiles from the atlas. So this visualization is SwissGL that is combined with WebAssembly module that runs like low-level C code that simulates 50 years old hardware. Yes, well, I guess that's all I prepared for today. I'm ready. Have some time for questions.
Is this Z80 work? Did you publish it already? Or?
So it's marginally published.
Okay.
It's published as a figure and a couple of paragraphs of text. So here, real-world instruction sets. There is little discussion where we say that we observe similar behavior. So we also tried 8080, but didn't write on that properly. There is link to this repository that uses WebAssembly that I showed. And then there is this figure that shows snapshot of the soup and highlights a few different instructions. Well, actually, what you saw here with this like narration and this history and with those assembly simulators that my colleague is working on is exactly, so this is, for example, visualization of how this replicator tries to copy itself over this program. But so it begins, and then suddenly, well, I didn't analyze yet properly, something happens that disturbs this replication process, and it ends up producing a very damaged replicator. And this is what like the mechanism of like extinction. Actually, if I with this simulation, where was it? Sorry. I can lab, yeah, in the lab, if I wait for replicator to appear and then disable noise, then we will see how these green replicators, well, there is still a little bit of noise. So those black pixels appear because of very rare mutations. They are just like 64 times less frequent, but but most of the soup is now damaged replicators, and there is very little life happening somewhere. But with noise, also this replicator is not particularly noise robust. It dies when there is a lot of noise. But another type of replicator, this LDIR, like MEMCPI based replicator, it's very noise tolerant. You can crank up the noise and it would still exist.
You have a ranking of those replicators, like if they compete with each other.
Well, of course, like stack-based replicators always lose to MEMCPI or to this stack exchange. But I didn't. I want to make a fight between stack exchange and MEMCPI. I would expect MEMCPI to win. But it's interesting to see how they discover the capabilities of hardware little by little. Like first they discover stack, then they discover, actually, a lot of the times when I want to figure out where does particular instruction, why a particular byte is in the soup, then it turns out that it's not because of random mutation, but because some instructions like function call puts the current value of position counter on top of the stack. And that's why basically it puts the address of the next instruction to be executed so that return could work. And then this is the way most of the interesting instructions are produced in the soup. Yeah, so this one is very noise tolerant. If I increase noise, it still manages to survive. Yeah. So I don't remember who was first. Yeah, okay, yeah.
Yeah, I think it's a great library. It's presented. I've got two questions. Number one says some more formal documentation. I didn't see the link.
So
Can you use that one?
there,
How you
so there is sort of documentation. There is this like README, which might be like slightly outdated, but not like catastrophically outdated. And there is something like an API that describes most of the keywords. And then there is a set of examples, but actually the deck I was showing, once it's completed, probably going to be the most state-of-the-art documentation. So I'm not proud of this library. I'm proud of principles I'm putting it, because implementation is awful. It's a mess. But my point is that actually, but it was quite easy to write. So it's more about trying to inspire people to write boilerplates that are compact. And on the other hand, well, basically, whenever people use like some huge library, it always like maybe you use 10% of this library. But then whenever you want something that is not there, but you need to use this library, you start with this framework, you need to write, I don't know, maybe a few times more code than in the case where you had a like lower level control. Well, or maybe, no, not more code, spend like many times, spend much more time. So yeah, like trying to make other things do something for you when it was not designed for you is longer than making it from scratch. And that's the point I wanted to like show. And so, sorry, there was a question here.
I wanted to ask, like, compared to like previous models like Tierra and Codeboard, like they tried to do like similar things, but they had to introduce the replication code, like they had to sync the program with the replicators. Like, what do you think we did differently here that doesn't need that?
So, I think Ettore is the best person, unfortunately not here, to ask comparison with previous results. So there were a couple of, I think, what was it called? Something begins with A from 91, 1891. What? Yes. So this is probably the closest. I think I might be wrong, but it relies on like functional. There were, I think, trees. Maybe I'm wrong. So there were experiments. So first, like actually, it's Blaise, our director, who was programming brainfuck in the nights, and somehow came to us saying, "Look at this fun thing," and it like itself like a worm that made a bunch of people at Google play with it rather than doing something useful and trying to implement different variants of it. So it spreads like a virus in this form as well. And then only then we started doing literature research and found a couple of works that are basically most of the time it's competition of existing replicators. But sometimes, well, there were a couple of works where emergence of replicators was demonstrated, but we think that ours is the simplest. So first of all, it's either special, like more complex instruction set, or, and in our case, BFF is probably the simplest you can get, or it's specially designed for a particular purpose. And I think I really love our old school CPU experiments because this demonstrates that you don't need to invent a new language. Hardware is around for 20 or for 50 years is also capable of doing this lifelike things. So there was another question.
Are you still interested in applying the Swiss principles to other languages like Python and so on?
Well, it's, there's this, if you're serious about software, you have to do your own hardware, because whenever yeah,
Okay.
yeah, because whenever I want to compute something, you always feel like universe can do this faster if you could build your own chips. So something I dream about is if one could make 100 nanometer chips at home. That would have been then there will be Swiss Verilog. Yeah.
The library doesn't allow now to load resources like meshes from.
Sorry, meshes are not, well, quadrilateral, instance tessellated quadrilateral is the only supported primitive. I was thinking about adding but well, there is this, on one hand, it may be added. On the other hand, I'm dreaming about having compute shader and no other types of shaders, and then writing rasterizer, efficient rasterizer that is, and well, for example, people do a lot of raycasting. Raycasting already became, ray tracing already became mainstream. And then do you have to stick with triangulated meshes if you can cast trace? Well, so textures are supported resources, and you can store geometry in textures. There are ways.
And what's the maintenance or longevity of the library? Because I do see sometimes Google dropping.
It's worse than Google. It's me dropping it.
Yeah, yeah.
But my point is, it's actually the proper way to use it. You copy it to your project, and then you modify it in whatever way suits your project. Maybe delete most of it and keep 20% that you needed, and maybe say that it's a stupid library and you write better one. Yeah.
Okay, thank you for the presentation. The demos inside the presentation in SwissGL was a nice touch.
I spent most of the time. That's why it's not ready.
Yeah, and what would you do if you want to store more than 4 values? I saw that data texture. Is there?
Well, first of all, you can. Proper way to do this is compute shaders, where you can run more general programs on GPU, but it's only available on web GPU. Web GPU will appear in browsers, hopefully in maybe it's now in Chrome, maybe in Safari. It's getting there. But on the other hand, there are texture arrays where you can store multiple layers. So that's how, if I need more than 4 bytes, then I store them in texture arrays, and then fragment program can emit up to 32 values. So you can have 8 layers, each of 4 channels. But then you can store state in multiple textures. You can have one texture for positions, another for velocities, another for some inner state of the particle, and then you can have, or you can have packed rectangles. Say you have adjacent pixels that store position, velocity, something. Well,
another quick question. I saw you added WebVR support in a couple of demos. Would it be trivial to render simulation on the inside of the sphere, for example, and then place the camera inside?
Yeah. Well, so WebVR support, last time I checked, worked for, say, on Oculus Quest, and in this standard. Well, actually, I wish I have brought this. For example, here I have this little WebXR. This is the deep simulator for debugging, but it looks quite nice, and it's implemented in a way. In library there is a hooks mechanism, so that every call you can add a hook and say that for every render call I will render 2 times for left and right eye. There is a little bit of magic, smoke and magic behind the scenes, but yeah, it's quite easily for sort of installations and.
Oh, we're having lunch. Good.